chi-squared tests in R and how to implement those. There's really two formulas that we're going to need. It's chi-squared.test and the q chi-squared, which gives our critical values. Just like this is the same as the q norm and qt and q binomial, and those all give us our critical values like we're used to. So we'll talk about that when we need to. So what I want to do is I want to go through the data that's taken from the 3 videos. These are the 3 videos that I've posted on our module for this chapter. And what I want to do is I want to show you how to run the tests in R. So I want to show you how to run these tests using the magic of R. So the first problem was taken from this video. This is the video where Sal is going to open the restaurant. So I've taken this data, I've put it in a table for us, and then I want to just run this test. And so I'll show you how to do that. So the first thing we're going to do is we're going to save our data. So x is going to be 30, 14, 34, 45, 57, and 20. And let's save our probabilities. Our probabilities are going to be 0.1, 0.1, 0.15, 0.2, 0.3, and 0.15. And it's important to know a few things here. If we add up all of our probabilities, we should get 1. If I look at the length of C and the length of the list of probabilities, those will be the same. Other than that, all we need is to run the chi-squared test of x against our probabilities, and it spits out, oops, I forgot to put in a command here, it spits out, x and probabilities are p equals probabilities, so it spits out our chi-squared value, which is 11.442, okay, which is the value that I found here, so 11.442, and then a p-value of 0.04329. And we wanted to test this. The wording of the problem is that we're going to test this with 5% significance. Since our p-value is smaller than 0.05, we reject the null hypothesis. So that's how that works. So for a goodness of fit test, generally what's going to happen is you're just going to have this one list of data, right? You're going to have this observed data here, and then you're going to compare that to your model, right? Whatever percent was expected. So it's a goodness of fit test. That's how you run that in R. Remember, one other thing I should say here is the degrees of freedom being 5. That's just the number of values. We had 1, 2, 3, 4, 5, 6. We had a list of 6 values, so that's just 6 minus 1. Okay. Also, number 2, so this is data taken from the second video. This is the video on the contingency tables, and what we're going to do for the contingency table, so for number 2 and number 3, so for the contingency tables and for the chi-square test and homogeneity, you have to input your data as a matrix. So I'll show you how to make a matrix. The commands for forming a matrix I've also put in R, so these are the values here. Okay, so that's the commands for making a matrix in R. And let's see, so the way that this is going to work, by a matrix, by the way, all I mean by a matrix is I mean a table. So this is going to be a matrix or a table, and let's take our data here. So let's get rid of that because I don't need that anymore. So we're going to have our data, and our data is going to be, I'm just going to read it off by row. It's going to be 20, 30, 30, 100, 110, and 90. The number of rows that are going to be in our table, there's going to be 2 rows and 3 columns, right? So we have 1, 2 rows and 1, 2, 3 columns. Also, the last thing that we need is I put in everything here by row. So I went 20, 30, 30, 110, 100, 110, 90. And so I'm going to put by row equals true. If you leave that value off, I'll show you what happens. let's call this value W. So if I leave this value off, you get a different matrix. So Y is the matrix that we've put all this stuff in by row. So we get the 20, 30, 30, 110, I don't know, I keep doing that, 100, 110, 90. If I look at the matrix W, it's going to put everything in by column. So it'll be, the columns will be 20, 30, 30, 100, 110, 90. Right? So it goes that way. We really want the data put in by row. So that's why I added that command. So always be sure to put in this command by row equals true. I always just like to print each of my matrices that I put in just so that I can have an absolute, just so I can be certain that I've input everything correctly. Kind of just graphically or visually makes it look a little bit nicer. And once you have your matrix, that's all you need for the test. You just do chi-squared test of y, and it spits out, here's your chi-squared test statistic. So this gives you a chi-squared test statistic of 2.5258. We have 2 degrees of freedom. Remember that the way that the degrees of freedom work here is that you take the number of rows minus 1, so it's 2 minus 1, or 1, times the number of columns minus 1. So this is 2 minus 1 times 3 minus 1, so that's really 1 times 2. So we have 2 degrees of freedom. And then our p-value is 0.2828. Since we were really testing this according to the video at the 10% significance level, that means that since our p-value is greater than 0.10, we do not reject the null hypothesis. So there's not enough evidence to reject the null hypothesis. Our final video is taken from this last video. Okay, so our final data set is taken from this last video. I just want to show you, so this is our last video, is the chi-squared test for homogeneity. And what we're going to do there, is we're going to test whether or not our populations are homogeneous, meaning whether they're really coming from whether they're the same or not, and whether there's any difference. So oftentimes this is the test that gets used very frequently, is if you want to have 2 data sets, you want to figure out whether 2 data sets are different or not. This test for homogeneity is one that gets used very frequently. This is the chi-squared test that gets used a lot in biology. So when you're studying evolution and you look at 2 different populations, you want to know, did their genetic makeup change from one generation to the next? Really, the technical thing that you're looking at is the allele count. You wanted to know, does that change from one generation to the next? So anyways, this chi-squared test gets used a lot in many places, but biology is one of the common places where this gets used. So let's go ahead and let's run the chi-squared test. This is basically going to work the same way that we did the test before. So I'm going to make a matrix, and our values for the matrix are going to be 24, 22, 14, 6, 8, and 16. There's again 2 rows and 3 columns, and I like to input everything by row, so I put that value in. So by row is going to be true. And again, just to make sure that I've input everything correctly and that everything is in the right order, I like to print the matrix Z, just that I can see that everything is going well there, so that I inputted everything correctly. And then we're going to just run the chi-squared test for Z. And from the chi-squared test for Z, we got our test statistic is 8.4. We have 2 degrees of freedom. Our p-value is 0.015. The way that the test was set up was at a 5% significance, so we reject the null hypothesis. And the last thing I want to mention in this video is how to find these critical values. So the critical values are going to be the cutoff points where this splits our x values, or the horizontal values, into a rejection region and a non-rejection region, just like we did for the t-test or the normal distribution. For critical values, what we're going to do is we're going to use Q for critical, and then chi-square, because we have the chi-square distribution. And let's say we wanted to find the critical value, 95% confidence or 5% significance. 2 degrees of freedom, because we have 2 degrees of freedom. And so what that'll do is that spits out our critical value, 5.991465. Since our value is to the right of our critical value, that means that we reject the null hypothesis. Okay, and so let's quickly just run over and look at the critical values for the other examples. So in our previous example, we were looking at chi-squared. Here, this was a 10% significance, so I'm going to change that to 0.9, but again, we have 2 degrees of freedom, so we get 4.60517. And then for our first example, we wanted to find the 5% significance, so our critical value there. Here we have 5 degrees of freedom, and so it turns out that that critical value is 11.07 and some change. Okay, so that is how the chi-squared tests work in R.